Hello everyone, welcome to my virtual talk on PMEvo, a framework for inferring port mappings of out-of-order processors using evolutionary optimization. My name is Fabian Ritter and I present research that I conducted with Sebastian Hack at the Saarland University Compiler Design Lab. Let's start by having a look at processor architectures. Early processor designs followed this traditional pipeline design. A stream of instructions is fetched and sent through the units of the processor to execute them one after the other. The instructions were loaded in program order and executed in program order. As programming language researchers, we naturally need to ask the question, how can we use this most efficiently? For such a traditional processor design, this requires scheduling instructions such that no data dependencies cause resources to idle, ensuring a full pipeline. Nowadays, and actually for quite some time, processors have grown a lot more complex than that. A still very simplified design might look like this. A key difference to the earlier design is that instructions are no longer executed strictly in program order. Instead, they are decoded into so-called micro-ops that are then handed to a scheduler inside the processor. This scheduler distributes the micro-ops among execution units that are grouped behind so-called ports. Each port can execute one operation at a time, but not all ports can execute all kinds of micro-ops. In such an architecture where instructions can be executed out of order, our search for performance becomes more complicated. Besides avoiding stalls from dependent instructions, we have another challenge. The processor scheduler can only work with the operations it gets. Our generated code can help here by using instructions that can be executed in parallel together. This, however, requires to know which instructions can be executed in parallel. Which operations the scheduler issues for simultaneous execution is dictated by what we call a port mapping. A mapping from instructions to their micro-ops and from micro-ops to ports on which they can be executed. While knowledge about the port mapping would ease our job in the pursuit of performance, hardware manufacturers typically keep these inner workings of their processors secret. This lack of information motivates our research. We want to infer a port mapping that explains the processor's performance characteristics. Since we cannot look into the hardware itself, we need to base our work on observations of the processor. So far, related work followed a common strategy for this purpose. They feed the processor with instructions under investigation and then read integrated hardware performance counters of the processor to count the number of operations executed on each port. For architectures where these counters are available, this is a reliable way of obtaining port mappings. With appropriately crafted experiments, inferring a port mapping from the counters is rather straightforward. However, such performance counters are currently only provided on Intel processors. To be able to infer port mappings for other platforms like AMD and ARM processors, we follow a different approach. We measure the instruction throughput achieved for specifically crafted instruction sequences to identify instructions that are executed in parallel. While these results cannot provide the same level of detail and are harder to interpret than reading performance counters, they can be obtained on any microarchitecture that allows measuring time, independent of the availability of performance counters. Let's have an example to see how such throughput measurements connect to the port mapping. Assume we want to execute an experiment without data dependencies, including two add instructions, a mul instruction, and a store instruction on a processor with a displayed port mapping. For simplicity, we assume that each instruction is executed as one micro-op. To see how this experiment is executed, we distribute the instructions according to the port mapping to the ports, represented by these buckets. An execution of the experiment could proceed like this. The mul and store instructions are forced to their ports, whereas the add instruction could be executed on either port 1 or 2. This execution needs 2 cycles, so we could assume a throughput of 2 cycles. However, when we add in another instance of the same experiment, we can distribute the instructions more evenly to execute the 2 instances in 3 cycles. On average, this leaves us with a throughput of 1.5 cycles per experiment iteration in a steady state. If the port mapping would allow other instructions to be issued to port 3, or would not give this freedom to the add instruction, we would obtain a different throughput. We can see that in the absence of data dependencies, the instruction throughput is solely determined by the port mapping. This already gives us the intuition that measuring throughputs can be helpful to infer port mappings. So let's investigate this connection further. If you want to systematically compute the throughput of an instruction sequence as it is determined by a port mapping, we have 2 options. One is to use a representation of this problem as a linear program. Using an off-the-shelf LP solver, we can compute instruction throughputs with a polynomial worst-case time complexity this way. The other option is to use our novel bottleneck simulation algorithm. We have proven it to be equivalent to solving the linear program, but with a time complexity that is exponential in the number of ports. This time complexity might not seem attractive at first glance, but for practically relevant port numbers, which are in the range of 8 to 10 ports for modern microarchitectures, our implementation is faster than a commercial LP solver for this problem by 2 orders of magnitude. So if our goal was to compute throughputs for a given port mapping, we would already be done. However, that's not our goal. We want to find a port mapping that explains the throughputs that we can observe on a machine. This problem might actually sound familiar to you. We basically need to black box learn a function, in the form of a port mapping, that maps instruction sequences to throughputs based on measured input-output examples. This is a classical machine learning task. The reason why we chose an evolutionary algorithm to solve this problem is that it naturally allows us to specify that our solution should be a port mapping, and all we need for good performance is a fast port mapping simulator without requiring things like gradients. It is not the only possible choice for this kind of problem, but the one that we found to work well. So our approach, PMEvo, uses a straightforward evolutionary algorithm to infer port mappings. It follows this outline. In the beginning, a population of individuals is generated randomly and their fitness is evaluated. In each new generation, a number of individuals from the population is selected to reproduce via recombination. The new individuals are also checked for fitness and added to the population. Then, the least fit individuals of the population are discarded to shrink the population back to its initial size. This is repeated until the fitness development converges. Now let's have a look at how we implement these steps. For our application, a population of port mappings is a natural choice. In the beginning, the randomly generated port mappings will not be particularly meaningful, but with each new generation, the building blocks will be newly combined to approximate the behavior of the processor under test more closely. We use a binary recombination operator in PMEvo. For each recombination, 2 parent port mappings are chosen to generate 2 new child port mappings. For each instruction, the corresponding micro-ops of both parent mappings are shuffled and split randomly among the children. In our example here, a possible recombination could have one child with micro-ops U2 from the left parent and U3 from the right parent, whereas the other child receives the remaining micro-ops U1 and U4. The fitness function is a crucial part of our evolutionary algorithm as it defines the objective of our optimization. Our fitness goal is to minimize a linear combination of 2 components. One is the average prediction error with respect to throughput measurements on a set of experiments, to guarantee that fit port mappings capture the behavior of the target processor well. We evaluate this with our efficient bottleneck simulation algorithm. And the other component is a measure of mapping complexity, so that the resulting port mapping is indeed concise and no unnecessary micro-ops are present. Clearly, a key to the quality of this fitness function is choosing a good set of experiments. While randomly sampling experiments to benchmark would be possible, we found our approach to generalize better to unseen input distributions when we construct our experiments systematically. 2 criteria are important for this process. The experiments need to be executed as freely as possible from non-port mapping related factors, such as data dependencies, and their throughput should be as characteristic for the port mapping as possible. To achieve the first point, we instantiate the operands of instructions to avoid dependencies as far as possible. For the second point, we use experiments that indicate whether and in how far a pair of instructions shares ports. By employing experiments with different instruction ratios, PMEvo can learn whether these instructions are executed in sequence, completely in parallel, or if something in between applies. To evaluate PMEvo, we use its resulting port mappings to predict the throughput of dependency-free code. We use 3 microarchitectures with 2 different instruction set architectures: Intel's Skylake and AMD's Zen Plus x86 architectures, and the A72 ARM architecture. Skylake is useful as a comparison with existing approaches, whereas automatically finding port mappings for the other 2 microarchitectures is out of scope for previous work. We compare the prediction accuracy of PMEvo's mappings to 4 other approaches. To the Skylake port mapping from UOPS.info, a recent work to infer port mappings from performance counters. To the Intel Architecture Code Analyzer, which may use proprietary information by Intel. To iThemal, a recent research tool that uses a neural network to predict the throughput of basic blocks. and to LLVM-MCA, an open source replacement for Yaka using LLVM scheduling models. Of these tools, the first three only come with support for Intel platforms. We therefore compare only on Skylake to them. Only LLVM-MCA has manually collected scheduling models for the other platforms. The comparison in prediction accuracy to the last three tools is a bit unfair, since our port mapping-based throughput prediction can only handle dependency-free code in a meaningful way. The other tools are intended as more general throughput predictors and might focus on different performance aspects. However, comparing to them gives us valuable insights into the state of port mapping modeling in contemporary tools. We report our prediction accuracy results in heat maps like this one. There will be a heat map for each tool for each supported architecture. This is the one for our approach, PMEvo, for Skylake. Each heat map displays the relation between the throughput we measured on the actual processor and the prediction of the tool for 40,000 sampled experiments. Each experiment is put into a bucket that is further to the right, the higher the measured throughput, and further towards the top, the higher the prediction. The darker a bucket, the more experiments are in it. Experiments close to the diagonal line are good, since they indicate that measured and predicted throughput match. For this heat map, we can see that PMEvo's port mapping gives predictions with high accuracy. Of the related work, Info, Yaka, and LLVM-MCA all show a similar picture. Their results are generally close to the diagonal line, which is a good sign for their prediction accuracy as well as for the quality of our throughput measurements. A curious detail that is common for all those approaches is a group of experiments whose throughput they underestimate with respect to our measurements. At first glance, this might look like a systematic error in our measurements. However, when we investigate these outlying experiments, we find that all of them contain bit test instructions accessing memory. A quick look into the throughput tables of Info gives us an idea of the problem. Their throughput measurements for these instructions, on the right of the TP column, are substantially larger than the throughput that they predict with their inferred port mapping, displayed on the left of the TP column. Together with the rather complex port mapping entry in the rightmost column, we have to conclude that some of these micro-ops contain data dependencies that cause the slower execution. Yaka as well as LLVM-MCA also have to be aware of the actual port usage, but apparently not of the dependencies, resulting in the visible underestimations. PMEvo cannot know anything about this disagreement between port mapping and throughput, and therefore infers a port mapping that does not contain this anomaly. Ithemel, the neural network-based throughput estimator, shows a different pattern with a lower prediction accuracy for our dependency-free experiments. This might be due to the difference in training data. Ithemel is trained with basic blocks extracted from compiled programs, which will naturally include a lot of data dependencies. For the other two microarchitectures, we can only compare to LLVM-MCA, since the other tools do not support non-Intel platforms. PMEvo's inferred port mapping for Zen+ displays a wider spread around the diagonal line, but still follows it closely. Compared to this, LLVM-MCA's predictions overshoot the measurements by a wide margin, indicating a less accurate and overly pessimistic scheduling model in comparison to Skylake. Notice the difference in scale. The ARM architecture shows similar trends. PMEvo's A72 mapping is more prone to underestimations, which might be due to the A72's less elaborate out-of-order engine that might prohibit optimal execution of the experiments according to the port mapping. LLVM-MCA's predictions here overshoot even more than for Zen+, indicating that LLVM-MCA might benefit from PMEvo's mapping, especially for non-mainstream processors. So what should you take away from this talk? Port mappings play an important role for understanding and improving the performance of a program on a given processor. By assuming that a processor executes instructions according to some port mapping, we can use an evolutionary algorithm to find concise models that capture which instructions a processor can execute in parallel. This is only feasible since we developed an efficient bottleneck simulation algorithm to evaluate the accuracy of a candidate port mapping with respect to measurements. The accuracy of the resulting port mappings in predicting throughput for port mapping dominated experiments is competitive where existing work applies and extends to other architectures that were previously out of scope for port mapping inference.